So in this video, and probably a series of videos, we're going to be reverse engineering a wireless video doorbell camera.
Welcome to Fresh Forensics, your go-to destination for everything Linux.
Hey everyone, welcome back to the channel.
So these are your low-end doorbell video cameras, $20, $25. You can see most of them, they look very identical to one another. Perfect project to reverse engineer, and that's where we are about to begin. So we're going to delve into the details of the one that I have specifically, but it's not really as much about that. It's more about the methodology. Most people probably are familiar with OWASP. It is a world-recognized nonprofit organization, and they have been instrumental in helping to secure the internet. They also have some very good resources when it comes to the testing of firmware. So I'm using this PDF. Once again, it's called the Firmware Security Testing Methodology. So whether network connected or standalone, firmware is the center of controlling any embedded device. As such, it is crucial to understand how firmware can be manipulated to perform unauthorized functions and potentially cripple the supporting ecosystem's security. To get started with performing security testing and reverse engineering of firmware, we're going to use the following firmware security testing methodology as guidance when embarking on an upcoming assessment. The methodology is composed of 9 stages tailored to enable security researchers, software developers, consultants, hobbyists, and information security professionals with conducting firmware security assessments. So the first stage is going to be information gathering and reconnaissance. So with that being said, I am going to pull up some pictures that I took of this video doorbell camera. This is what it looks like over here on the left. I have a couple of them. Works fairly well. You download an app for your phone, and through that app you're able to communicate with the video portion of the doorbell, and you can watch what's going on and you can receive alerts, etc. and so forth. So that's what it looks like on the left, and this is what one looks like when you start tearing it down on the right. So I opened it up, took the batteries out. Here's one of the antennas. Here's another antenna. What I really wanted to get to is this board right here. This is the focus of attention right here. This is where everything lies that we are interested in. This is the backside right here. And if we look closely, this is the main chip right here. This is a SoC, system on chip. We can read the information off of that. So I did get some more information on the chip and the manufacturer. Probably of more interest to me than that is going to be this right here. So this is going to be the SPI flash chip, and this is what is going to hold the entire operating system, whatever that operating system is, as well as the bootloader. And we are definitely going to attempt to extract contents of that using a programmer. If you look real close here, okay, right next to the main chip, you can actually see that there are 1, 2, 3 little dots right there, and they're labeled. So you can see this one says ground, this one says RX, and this one looks like it might say TX. And that is what it says. So we have an RX, a TX, and a ground. That immediately got me excited because, especially considering how close it is to the main chip, it's right next to it, that this might allow me to get a shell on the device. It kind of did. So once again, we will explore that momentarily. So I'm giving you guys a couple teasers here. So just hang on tight. We're going to get into the good stuff. Here is another view of the board, and we can see more clearly the SPI flash chip right here, and you can see that it says XMC on it. It also is very close to the to the main processor on the board. Next thing is going to be the FCC ID. So if you look at the side of the camera housing, it's very clear there is an FCC ID right there. So we are in the reconnaissance phase of this, called fccid.io. And I'm going to click on that. And this is usually a much faster way to find what we are looking for. So I'm going to paste in the FCC ID that I got off the side of the camera, and we're going to do a search, see what comes up. And we do get something back. So we have a video doorbell. When we're talking about any device that transmits any type of signals over the air in the United States, it has to be registered with the FCC. And this is a valuable resource for security researchers, reverse engineers, etc. and so forth. We have the actual user manual for the device, and we have test setup photos and label locations and internal photos, which can definitely be very valuable, especially if you are not trying to open up something. So here are photos of the inside of the device. Here's some close-up pictures of the board. This is actually how I originally found the TX and the RX, was because I was able to see it a little bit more clearly on these pictures than I was able to see in real life. But there's not a whole lot more that I would say is of value on this site for this particular product. I was hoping to find maybe a layout of pins or pads, and there wasn't anything like that. Sometimes there is, sometimes there isn't. Definitely a good resource to be aware of. This is some information pertaining to the main SoC, the All-Winner V series. Once again, we're in the reconnaissance stage of this, so we're just gathering as much information as we can. And I did manage to find a very long data sheet. It's over 400 pages long. Okay, so if we go back to our firmware security testing methodology, we're looking at stage 2, obtaining firmware. So we want to try to obtain the firmware using one or more of the proposed methods listed. There are numerous ways that we can obtain the firmware. Though many of those are listed here. Some of them include sniffing serial communication within hardware components for update server requests, dumping the firmware from the bootloader, removing the flash chip. We're not going to remove the flash chip. We are going to pull the firmware from the flash chip. And I did want to take a look at sniffing serial communication by looking at the TX and the RX pins. I figured out a way to connect to these little tiny pads over here. Wasn't worried about the ground as much as I was with the RX and the TX. They're too close together. So for the ground, I used this more copper looking pad over here, but I needed to get to the RX and the TX.
A UART channel has 2 data lines. On each device, there is an RX pin and TX pin, RX for receive and TX for transmit. The RX pin of each device is connected to the TX pin of the other, and vice versa.
So what I did to do that was I used some tools referred to as PCBite probes, and these are instrumental in being able to get some of these connections up and running because they're so small and I can't solder. I cannot solder if my life depended on it. So these PCBite probes are very, very important, and I'm going to show you what they look like real quick. So you have a couple different kits. Higher end one would be this one right here. So with the aid of these PCBite probes, as well as what is referred to as a USB to TTL adapter, I am attempting to get a shell on the device. So the PCBite probes, they ultimately connect to wires. Those wires come over and they connect to the USB to TTL adapter. This is actually the adapter that I'm using in this particular example right here. This is the USB to TTL adapter. It's about $15. And you can see on the front part of the adapter, on the left-hand side, you have the RX, the TX, the ground, and the VCC. We're not concerned with the VCC. You're concerned with the ground and the RX and the TX. What we are trying to do is get shell access to the device over serial. If nothing else, if we can't actually get access, if we can't get a root shell on the device, then at least to see the logs, the boot up logs when we power the device on. So there's a lot of moving parts to this, and one of the things that goes with this is, unlike using the EEPROM BIOS programmer, you need power for this. You have to actually power the board up. I have an adapter plugged into the board with a switch so that I can click that switch and it'll power the board up. I'm also going to connect to the video camera from the app on one of my other phones. And by connecting to it, that'll keep the camera open and it'll keep everything on the board running, which will produce more logs. I'm actually mirroring the screen of one of my phones that I'm using as a camera. And this just makes it easy for me to do all of the recording for this. Okay, so here is my Kali Linux workstation. And we have the USB to TTL adapter plugged into the USB port. We have 3 wires running out of it. The green wire is ground, and the blue wire is connected to the RX pin on the adapter, and the yellow wire is connected to the TX pin. So when we follow those wires over here to the PCBite probes, we can see that we have 3 PCBite probes all connected to pads on the board of the IoT device, and then right here is the switch just connected to the board, giving the board power. So when I click this switch on, it'll power the board up, and then we should see some logs being produced. So I'm currently connected to that laptop via SSH, and I can cat out the contents of the etc OS release file, and you'll see that I'm running Kali Linux 2024.1. And if I do ls USB, that will list out the devices that are connected to the laptop via USB. And one of the things that you see is the USB to TTL adapter, which is also referred to as an FT232 serial adapter or a UART adapter. Now, if you've never done this before, there's a couple of important things to understand. Perhaps the first thing you want to do is you want to determine where on your Linux system this adapter is, the node that it's connecting to and being recognized as. So the easiest way to figure that out is to just run dmessage. So if I run dmessage with sudo privileges, we can find the USB to TTL adapter right here. So it says FTDI, this is the adapter, and we see that it is connected to TTY USBO. So that's where it's being attached to on the Linux systems. That's very important to know. So I'll go ahead and copy that information. And we're going to be using a tool called minicom. If I do an apt info on minicom, we get back that it is a clone of the MS-DOS telex communication program. It emulates ANSI and VT102 terminals, and it has a dialing directory and auto Z modem download. Basically, minicom is the command line utility that we use to get serial access to these devices. And I can pull up the help menu by running minicom --help. One of the main things that we're going to need to know is the device. That's what I got from dmessage. So we're going to do a capital D for device, and we'll give it the location in that file system, which is /dev/tty usbo. We are also going to have to set a baud rate with -b, and typically with these devices the baud rate is it's usually 115/200, and then if it's not that, it's 9600, but I already know it's 115/200. And then the last thing we're going to do is we're going to do a -C for a capture file, and we're going to capture all of the logs to a file so that we can go back and examine the logs later. And I'm also going to do a -w for line wrapping, just to make things a little bit easier on the screen with the output. So with all of those things in play, let's go ahead and start up minicom. We're going to run minicom with sudo privileges. We're going to do a -D and give it that location in the file system that we got from dmessage, which is dev tty usb0. We're doing a baud rate of 115/200. We're going to do a capture file. We're going to call it Bootlogs.txt, and I'm going to do a -w for line wrapping. Go ahead and start that up. I'm going to attempt to transmit data, or in other words, communicate with the device and not just see the logs. And to do that, I'm going to make sure to do a Control-A-Z. That'll pull up the options for minicom, and I'm going to turn on echo by pressing capital E. And now echo is on, so if I type hello, it allows me to see that being typed into the terminal. I'm going to open up the app on my phone for the camera and get that up and running as I power on the camera. So I'm going to power the camera on right now, and hopefully we see some logs. And immediately we are getting a lot of logs on the screen. If I try to communicate with the device, however, it is not letting me get access to it. That's okay. Now you see more logs are flowing by on the screen, and that's because I just now made a connection to the camera. So I'm actually connected to the camera right now, and by doing that, that keeps the board powered on and keeps the board active, and we continue to see logs. Otherwise, it would have capped out at 100 lines, and that would have been the end of it. Okay, so I think I have produced enough logs. Now I'm going to close the app on my phone, and that's going to disconnect from the camera, and we'll probably see an end to the logs. Okay, so to exit out of minicom, you're going to have to do a key combination. You hold down Control and press A and then hit X, and it will ask you if you want to leave minicom, so I'll hit enter for yes. So now we have exited minicom, no longer have any need for the camera to be powered on, so I'll turn that off. Let's go ahead and open up the bootlogs file and take a look at what we have. So we see the device booting up and loading addresses into memory space. We see various processes identified as PID 405, 407, 408, 409, starting up, things being mounted, directories being created, normal stuff. There is a binary that starts running. This is a binary we will look at more closely later on. And we have our init.d scripts that start up, typical of any IoT device. And if we go a little further down, it is attempting to, it appears that it's starting a shell on the console. So I should be getting access to it. I don't know why I'm not, but it definitely is starting up a shell. And then BusyBox starts up with its built-in ASH shell. So BusyBox version 1.27.2 starts up, and then we get our banner for Tina Linux. Tina is based on OpenWRT, and it is described as Tina Linux Neptune. And Tina Linux is an embedded software system for intelligent hardware products developed by Allwinner Technology based on the Linux kernel. Tina Linux is based on OpenWRT version 14.07 of the Software Development Kit, which contains the kernel source code, the drivers, the tools, the system middleware, and application packages used in Linux system development. So this is great. So I was able to learn some more about this Tina Linux operating system that's running on this camera. We get the firmware version 1.7.9, and from there we begin to see a lot of IP address information. We have a connection being made to perhaps a server in the cloud at this endpoint. We got some peer-to-peer server connections being made on various IP addresses and port numbers. We have a thumbnail that is apparently being saved and sent to this IP address over HTTP. That would be interesting to take a look at. And we have a command server keep alive connected to this IP address and port number. We found a lot of IP addresses inside of this bootlog file. So many that I think that they deserve a closer look. Now we can use regular expressions and run grep from the command line. I've messed around with a few different regular expressions, and the one that seemed to work best for me was the one right here that I have on the screen. So if we run that, we get back a very lengthy list of IP addresses. Most of these are probably repeating themselves. So we can rerun that command and pipe the output into sort with a dash lowercase u, and that will get rid of all of the repeating IP addresses. Now we have a much smaller list. In fact, if I pipe that into word count, the dash L, you can see that that's 13, which is a very, very big difference from the first time that we ran this, which was 134. So we have 13 IP addresses. Some of these are going to be IP addresses on the internal network of the test network that I created for this IoT device. With the help of ChatGPT, I created a custom bash script. I call that bash script Lookup.sh. All right, so I'm going to run this bash script. I'm actually not connected to the internet. This is what it looks like if you are not connected. So it'll still pull all of the IP addresses from the log file. It prints them to the screen, and discovered I wasn't connected. It lets you know you're not connected to the internet. Now I'm going to connect to the internet. And let's go ahead and run this again. All right, now let's take a look at the output. We'll go back up to the top. So it gives you a listing of the IP addresses found in the log file. It gives you a count. It found 13 IP addresses. We do an internet check. We are connected to the internet. And then it proceeds to run geoip lookup and who is on each one of those IP addresses, and it prints the results to the screen. We see that most of these originate in the United States, and a lot of them go back to Alibaba Cloud, which is a particular type of cloud infrastructure. And if we go down closer to the bottom, all of these IP addresses don't return the info because they're internal IP addresses on the test network. And then at the very end, it will let you know that your results have been saved to a file, and this is the name of the file. Once again, it's deriving the name from a combination of a couple things. One of those being the name of the input file, which was bootlogs, and then it's adding results. And then in addition, it's adding the current date and time. So every time you run this command, it should produce different results because of the date and the time portion. So we can go ahead and cat out the contents of that file. And because of the colorization rules that I added to it, they will still be applied even to the .txt file, which is one of the things I really like about this script. I'm going to post this bash script on my GitHub page. If you're not familiar with that, it is located at github.com/Douglas Fresh Habian. I am going to upload the firmware to the repository so that you guys can follow along with me on any of the next videos. I'm also going to upload the bash script that I just demoed for you guys, and I will also update my PDF library and add the firmware testing methodology PDF that we are making reference to in this series of videos. So I will make sure to do that as well. In the next video, we are going to extract the firmware from the board. We're going to analyze the firmware image. We're going to extract the file system from the firmware image, and then we're going to begin to analyze the file system inside of the firmware image.
If you found this video helpful, don't forget to like, comment, and subscribe for more Linux, cybersecurity, and hacking content. And as always, keep learning
and stay fresh.
I'll see you in the next video.